we've started to talk about this rule of V's, relationships between the map pattern of rock units and the strikes and dips of rock units. So there's a handout that I will put on Blackboard, and I'm going to just go over here. And so it starts out by showing this. I'm just going to kind of go through the figures here. So it starts out showing these two blocks. So these two blocks have the same maps, the same surface, this top part, the same exact pattern. What appears to be a thin geologic unit and steadily thicker geologic units dipping. If this is north on the far side, these are dipping to the east. They're all dipping the same. So we can generate this pattern by changing the thicknesses. This seems kind of intuitive. So what's a little less intuitive is we can generate the exact same pattern by taking a bed of the same exact thickness and just having it dip at different amounts. So if it's vertical, we see the true thickness on the map. And if it's tilted so it has a very low dip, it intersects the surface and it makes a very wide area on the map. And so it's important when we're looking at the map to know, which of these situations we're dealing with. And in a moment, I'll show an example from the New York State map where we're looking at this situation here. So the extreme version of this is you have horizontal beds, and then the entire surface will just be all the same unit. That doesn't mean that the unit is, extremely thick. It could be very thin. It just happens to be that the surface of the Earth is just exposing that thin layer. So the other thing to note is that on this diagram, none of these thicknesses are actually the true thickness. When we talk about the thickness of a rock layer, we mean measured perpendicular to the layering. So we would just do a little bit of trigonometry where we could calculate, knowing the dip and the map thickness and the topography, which in this case is just a flat horizontal surface, we could calculate the true thickness. So we're not going to actually go into that calculation, but it's pretty simple if you know some trigonometry. So here we're looking at the state geological map of New York. And there's this area here where you have, so each color is a geologic unit. You have this area with huge, so this and this here, this is 40 miles. You've got 50-mile wide areas that are the same rock unit. This color green or this sort of greenish tan color. So that doesn't mean that the rock layers are like tens of miles thick. They just happen to be flat, and you can see that in the cross section here. So this cross section, I think, starts up here somewhere and comes across to the New York City area. So when it goes through this whole area in the middle, you can see there's a big sort of syncline shape, and that the rock layers are fairly horizontal. And when our field trip will be sort of up in this area, thinner rocks, and those actually will, as you'll see, are dipping a lot steeper. So continuing on with this handout that I'll give you, if you want to know the true thickness, you can, if you look at it down sort of in the direction of dip. So here's and then look at that. So he's looking down the direction of dip. what you'll see is this, and that thickness you see is is really the true thickness. So when you're in the field or looking at a map, you can align yourself in such a way that uh, you're not getting, in most cases it won't work for horizontal or near horizontal, but you can align yourself so that you could sort of see the real thickness. And that same principle is used, like if they write on a road, sometimes you're coming at a really low angle, they'll write out these big letters so that far away they look, if you tilt your computer screen, this might look more normal. Okay, so there's some information about areas with topographic relief and the rule of V. So we brought this up, but it's worth having something to read and talk about this a little bit more because it's important. So it goes through sort of the rules. We'll look at the examples. You can read this on your own. Okay, so here's the first example. Bed, the gray bed is horizontal. This is a topo map. So they've got a stream here, and the way that they show which way is downhill and that this is a valley is that the stream ends. So usually streams don't go to the very top of the hill. They usually start halfway down. So here is a three-dimensional sort of perspective of the same thing. So you can see that with this horizontal bed, it's not dipping. It makes a V shape, and the beds follow topography. So we've talked about that before. That was in the Grand Canyon lab. Okay, if it's dipping downstream and steeper than the stream, which is often the case if it's dipping, streams don't tend to be dipping that much. So we can pretty much make a rule that the bed, when there's a valley or a stream, that the point, sort of, if you think of this as an arrow pointing, it's pointing to the west here, that the bed, this dark gray bed, is dipping to the west. And the same thing, if it's dipping to the east now, with these maps, north being up, so we see the map pattern is pointed to the east, and it's dipping to the east. So that's sort of the rule of thumb, and that's only going to really be rare cases where that doesn't hold up, and we'll show an example of that at the end. Okay, so this is I guess this is actually one of those examples. So here it is dipping to the west, but the pattern shows it to the east, and that's because the dip is very shallow and less than the dip of the stream. So that's kind of unusual, and let's not really worry about that, but just know that that's possible. And the link that I sent you to the Steve Reynolds sort of like videos where you can change some of them, you can change the dips and you can play around with this, and that is totally worth doing if this isn't intuitive to you. Okay, we've seen this figure before, and now you see it in context. So here's map patterns. Here's the symbol for horizontal beds. What we were just showing, horizontal beds follow topography. These are valleys dipping to the north. You can see it's dipping in the north. The arrow sort of points north. Topography has no influence on it. Means it's vertical. There's that vertical strike and dip sign. Dipping south, you can see how it's dipping from the side there. It's dipping to the south towards us. Arrow's pointing south. Here's a case where the beds are dipping exactly the same as the stream. You get this kind of weird thing where there's no V. And then here's that exception case where the beds are dipping very shallowly and actually pointing the opposite direction from how they're truly dipping, which is truly dipping south, but it points to the north. So this is the exception. And it's not going to happen. You're not going to see that very often. Okay, and here's another presentation of the rule of V's, just a different author. So here we have map views again, but they've shaded it instead of putting topo lines. So what you're looking at here is this valley. The stream is flowing south. Personally, I find the shading hard to see. It looks like this was this looks more like a hill to me. But sometimes if you look at it from a different angle, from a different side or upside down, you can see it. But so this is a valley. And here again we have, it shows, oh, these rocks are dipping to the north, and there's the V pointing to the north. And you can see it on this diagram. Same thing here, V pointing south. You see the beds are tilted to the south. And then this example again of, okay, if it's vertical, there's the vertical dipping bed. On the map, it just is a straight line. And you can ignore it. We've seen this in the lab. This is how you can calculate apparent dip, but we've already talked about that.